let us continue our study with subspaces. So, let always K denote K be a field and V be a K vector space. Before I recall a definition of a subspace, we need to recall, let us first recall definition of subgroups of a subgroup of a group. Let G be a group and a subset H of G is called subgroup of G if the binary operation G cross G to G of G induces a binary operation on H, that is the restriction H cross H to H is a binary operation on H. This means with the same binary operation H is a subgroup, H is a group in its own right. So, easy way to check this is let us record this in this what is called subgroup criterion. Let G be a subgroup, G be a group and H is a subset of G, then H is a subgroup of G if and only if one identity element of G is an element in H, two, whenever if A and B are elements in H, then AB is an element in H and A inverse is also element in H. So, this condition 2 is also reformulated as 2 prime if A comma B is in H, then AB inverse belong to H. Instead of these two parts AB belong to H and A inverse belong to H, we can combine this and just write AB inverse belong to H. I will leave it for you to check this equivalence, which is very easy. but I want to immediately note the following consequence. Intersection of arbitrary family Hi of subgroups of G is again a subgroup of G. This is immediate because condition 2 is very easy to check and condition 1 is obvious because identity belongs to each member. So, identity will belong to the intersection. So, also I want to note the following consequence. So, corollary to this consequence is the following. For each family of elements, for every family I in I of elements in a group G, there is a smallest subgroup of G containing these elements, containing all I in I, smallest, because you consider all subgroups which contain all these AIs, there is definitely one subgroup which contain all of them, namely G. So, there is, we can take intersection, and intersection will be a subgroup of G by the above consequence. So, for each family we have a subgroup which containing all these elements. This group, this subgroup is said to be generated by AI. And the family AI in I is called the generating system, a generating system. Of this subgroup. So, in this case, we denote this subgroup by H AI. Let me justify this notation. Let me first take the simple case to illustrate. So, suppose the indexing set was just singleton, let us call it 1. That means there is only one element we are considering, let us call A1 to be A. So, this subgroup just contains the powers of A, that is H singleton A is nothing but A power n varies in integers. If you are using the additive notation, then one should write it as n times A. This is in a multiplicative notation. This is additive notation. So, in this case it is a cyclic subgroup. Generated by A and A is a generator of this subgroup. If your group is commutative, suppose G is commutative, G is abelian, then in this case the subgroup generated by the family AI, remember we have defined it as the smallest subgroup which contain all these guys. Is precise, you can describe the elements of this subgroup as the additive notation I will use, it is a finite sums like this. I belong to J and J is a finite subset. So, J finite and ni's are integers. So, finite Z linear combinations of the family AI is precisely the set of all elements in the subgroup generated by this. You can also use the notation this is nothing but summation I in I Z AI. So, this justifies also the name the terminology that subgroup generated by a family AI. Okay. If you have I is a finite set, if I is a finite set 1 to n, then H A1 to AN, this is precisely Z linear combinations of A1 to AN. This is the notation for all Z linear combinations of A1 to AN. All right. So, I also want to note here one example. If you take the simplest group Z G equal to the additive group of integers, this we know that this group is cyclic, then G is cyclic, generators generated by 1. So, in our notation Z is H of 1, or also this is same as H of minus 1, because minus 1 is also generator. In this group, all subgroups are also cyclic. You can write more precise statement. More precisely, for every subgroup H of Z, there exists a unique natural number n such that H is the integral multiples of n. Just one word about the proof. The natural choice for n, so take n equal to a minimum of H intersection n. Note that this minimum exists because of the well ordering principle for n, and now it is easy to check that this n, easy to check that H is precisely multiples of Z. For this equality, one inclusion is obvious. This inclusion is obvious because n is in H, therefore all multiples of n are in H. Conversely, for the other inclusion, use division algorithm, division remainder. And I will not write the details here. Even though I have not written here, some of these details you can find in supplements which will be uploaded here. Okay. So, two more things I want to note for finitely many, still in the same group of additive group of integers. If I have finitely many integers a1 to an, let us assume they are non-zero natural numbers. Whenever I write n star, it is n minus 0. Then the subgroup generated by a1 to n we know, we have just seen that every subgroup is finite, cyclic. Therefore, this subgroup is also cyclic. Then how do we find the generator? Finding the generator is very easy. This is almost immediate from the definition of greatest common divisor, that this subgroup is nothing but generated by GCD of a1 to an. This is almost immediate from the definition of a GCD, and the intersection of the, to take the subgroup generated by A1, that is all multiple or integral multiples of A1. If I intersect this with A2, subgroup generated by A2 and so on, this subgroup intersection of subgroups, so it is also subgroup. Right? Oh, sorry. So from where?
From the start.
Okay.
Just no. Beginning of this line.
Yeah, I will repeat this. Shall I start?
Yes, you will.
Okay. Shall I start? Okay. If you take cyclic subgroup generated by 1, cyclic subgroup generated by 2 and cyclic subgroup generated by n and take their intersection, this is also subgroup of Z. The generator for this is nothing but the LCM. Both these statements are just immediate from the definition of LCM and GCD. Okay, now let's come back to subspaces. So, a subset U of V, let me remind you, V is a vector space over a field. A subset U of a vector space V over a field is a subspace of V with the same addition and scalar multiplication induced from V, U is a K vector space. In this case, I will also say that the K vector space structure on U is induced by the given K vector space structure of V. As in the case of subgroup, we can also write a subspace criterion. So, let U be a subset of V, then U is a subspace of V if and only if three conditions. One, the identity element in the abelian group V plus, which we are denoting 0, that should be in U. 2, if the vectors x, y belong to U, then their sum x plus y belongs to U. And third one, if A is a scalar and x is a vector in U, then the scalar multiple Ax of x also belong to U. So again, I will not write the proof for I will not write the formal proof for this. Proof easy to write. You can also see the proof in the notes. So I want to save some time to skipping such proofs. All right. As in the subgroup case, we also have the following consequence. Intersection UI of an arbitrary family UI I in I of subspaces of a vector space V is also a subspace of V. Note that I could be infinite index set, so it could be really infinite infinite family of subspaces. Also here I should note that strictly speaking I should also keep that K in the notation and write it instead of a subspace K subspace, just to remember the field we are working with, but most of the time I will drop this K in the notation. Okay. Now I want to see, so this is again checked by using the above conditions 1, 2, 3, and all of them are easy to check. Okay, now I want to also discuss many examples now, so that where is the color? Oh, here. Okay. Okay, some examples from possibly from different branches of mathematics. Okay. Number 1. In these examples I will always denote K to be a field. When I specify explicit field, then I will mention that term. So every K vector space V has two trivial, we will call them trivial subspaces, namely singleton 0. Remind you, 0 is a 0 vector which is called 0 subspace. And the whole vector space V. These are called trivial subspaces. In particular, if V is K, then K has only trivial subspaces. So that means if U is a subset of K and if U is a subspace, then either U is 0 or U is the whole K. So just to note here, if U is non-zero, then it will contain some non-zero vector x. But this x is now vector and it's also scalar because v equal to k. So x is in k, x is non-zero, so x inverse exists, and so x inverse times x, this should be in u, but this is 1. Once 1 is in u, a times 1 which is a which is also in u. Therefore, every a is in. So, therefore, so that is k equal to u. Okay. So, we will have a break and then continue in the next half.